We will now begin some sample numerical solutions of flow over a flat plate. Until now, we have been doing a lot of theoretical work with boundary layer theory. So how does an engineer apply it in practice? So we said Blasius came up with a numerical solution for viscous flow over a flat plate. Now we are going to apply it to a practical problem and get some numerical solutions to show you how these things are used. So we first write down the closed form expressions that Blasius got for a laminar viscous flow over a flat plate. This is the theory that we briefly discussed in our previous video. It's also derived in detail in our textbook. So this is the results. This is a starting point for our subsequent work. So here is an example. So we are given a flat plate at zero angle of attack. It's a three-dimensional flat plate, therefore it's got a chord of 2 meters, span of 20 meters. Think of it like a wing of span 20 meters. The chord is 2 meters. It's not an aerofoil, it's just a flat plate, zero thickness. It's flying in a standard atmosphere conditions, so we can look up the pressure, temperature, and viscosity. Now, first thing we need to do in all these problems is, if they give you the information and velocity, we are going to look at velocity, two velocities. One is 100 meters per second. The other one is a higher velocity for Mach number effects, compressible flow effects. But it says, first thing we do is find the speed of sound, find the Mach number. If the Mach number is low, we can assume incompressible flow. Then you take the rho infinity, which is 1.22 kilogram per meter cubed. This way, this flat plate is flying at 100 meters per second, so that's V infinity. It's got a chord of 2 meters. Look up the viscosity, from a supply table, or in this case, it is given. So you can solve for the Reynolds number. So the Reynolds number is 13.6 million. So the skin friction coefficient is this expression. So when you integrate the CF with dx, you'll get a 1.328 times square root of nu over V infinity times capital L, which is L is the flat plate length. So the CD would be 1.328 divided by square root of Reynolds number based on the L. Anderson also calls this CF, so I'm using the symbol CF, but correct way of thinking of this is the CD, because this varies with X every point, whereas the CD is an integrated quantity, integrated over the entire X from X equal to 0 to L. So this is the drag coefficient. Now drag on the flat plate is 1/2 rho infinity square times chord, which is 2 meters, 20 meters of span, so 2 times 20 times the CF is the drag force on one side of the flat plate. Since we have an upper surface and lower surface of a flat plate, you just multiply this by 2, then this is the drag force for the flat plate. If somebody asks you what is the thickness of the flat plate at the trailing edge of the boundary layer, all you have to do is 5 over square root of Reynolds number. So we know the Reynolds number is this one. We can solve for del because L is 2 meters. It's 2.712 millimeters. So it's a very, very thin boundary layer compared to the length of the flat plate, which is 2 meters. So 2 meter span chord, only 2 millimeter thick boundary layer. So boundary layers are very, very thin animals, but they do a lot of damage. They cause skin friction. They can also cause flow separation, as we will see later. Now let's look at a second example. Turbulent flow. Later on we are going to see the turbulent flow. We are going to show these expressions empirically. We won't compute them. This is from measured data and some analytical / numerical solutions. So let's apply the same principle to this problem. So now you have to integrate this CF with respect to x instead of the previous CF. By the way, in homework number 1, you have some practice doing these integrations. So we are going to take a Piper Cherokee wing. This is the span, this is the chord. This is miles per hour, so you have to convert that into meter per second, sea level. So we want to compare the laminar flow and turbulent flow. Laminar flow part is easy because we just did it for a flat plate. So find the CD. Compute the Reynolds number first. Compute the CD. Then 2 times 1/2 rho infinity V infinity squared. Rho infinity is here. V infinity squared. CD times chord times span is 38.4 newtons. In turbulent flow, you'll have to integrate this expression of CF with respect to x. So if you integrate it, you'll get this expression. In homework number 1, you're asked to perform the integration and get this values. So if you have done homework number 1, you may be familiar with this. So use this CD with the Reynolds number of 6.93 million instead of this CD. So you'll get a higher CD, then put that in here, then you'll get a higher drag. So the turbulent flow has got 6.25 times more drag than laminar flow. So on one side we have 38.4 Newton, roughly 40 Newton. Here you have 240 Newton, 6 times more. That's why turbulent flow is tremendously draggy compared to the laminar flow. How thick is the boundary layer? Laminar flow for this case is 5 times chord over square root of Reynolds number. Delta over C is pi over square root of Reynolds number is 3.04 meters. For the turbulent flow, delta over L is 0.371 by Reynolds number based on the length of the chord of the wing, airfoil, raised to power 1 over 5. So if you plug in, you get a thickness of 25 millimeters. So turbulent boundary layers are much thicker than laminar boundary layers. They are more drag than laminar boundary layers. So now let's say what happens if you have a transition occurring when the Reynolds number equal to 500,000 based on x. So rho infinity V infinity times x over viscosity equal to 500,000. So we have the rho infinity here. V infinity is 100 meter per second times x over mu infinity equal to 500,000. So you can solve for x. Then x over L will be you can solve for x. So you have to just integrate it 2 times from 0 to 0.1154. You should use the laminar based drag force, drag coefficient integrated. Then from 0.1154 to the chord length, you should use the turbulent integration. Again, in homework number 1, we do integration of this nature. So if you integrate all these things, you'll get a net drag per side of 230 Newton rather than 240 Newton. Because part of the flow was laminar, it was not all turbulent, you get lower drag. So if you could make the whole airfoil laminar, you'll get 40 Newton. If the whole airfoil was turbulent, you'll get 240 Newton. If the airfoil is transitioning, you get between the two numbers roughly 225 Newton. So this type of numerical problems you are now able to do.